Today we are going to be talking about solving for the total response of an RLC circuit. You may recall from circuits 1 that the total response of a circuit is the combination of the natural response, which we've already determined how to find, and the forced response. And the forced response was simply whatever the circuit parameter, be it the capacitor voltage, inductor current, etc., settled to at t is equal to infinity. So we're going to work an example problem that will hopefully illustrate the changes to the process in solving for the response of an RLC circuit that need to be included to get the total response. So we're going to be looking at this circuit here. We can tell that this is a total response problem because this 12-volt source does not actually get removed from the circuit when this switch opens. The switch here that opens at t is equal to 0, all it does is take this 5 ohm source out, leaving behind a 1 ohm resistor in series with a 1/2 Henry inductor in series with a 2 farad capacitor. So we can see that this is a series RLC circuit and that it will be a total response problem. So we're going to start off, as we normally do, by calculating alpha and omega naught. Alpha for a series RLC circuit is defined as R divided by twice L, which in this case that's 1 ohm divided by 2 times 1/2 of a Henry. So 1 divided by 1 gives us 1 Nepper per second. Omega naught is 1 over LC, and we take the square root of the whole thing. So that's going to be L is 1/2 of a Henry. C is 2 farads. And then we take this whole quantity to the negative 1/2 power. And so that's going to be the square root of 1 over 1 is 1 radian per second, which means that our circuit is critically damped since alpha is equal to omega naught. Now we're going to analyze the circuit at t is equal to 0 minus. So at t is equal to 0 minus, this switch is closed, and we are at DC steady state. So our 12-volt source will be there. Our 1 ohm resistor will be in. Our inductor will look like a short circuit because we're at DC steady state, where this will be our inductor voltage, VL at 0 minus. This will be our inductor current, IL at 0 minus. Our switch is closed, which means our 5 ohm resistor is included in the circuit. And our capacitor will be replaced by its DC steady state equivalent, which hopefully you recall is simply a set of open circuit terminals. So here's our capacitor voltage, VC, at 0 minus, and this is our capacitor current, IC, at 0 minus. So by inspection, we can see that VL at 0 minus must be 0 volts because the voltage drop over a short circuit is always 0. Similarly, we can see that IC at 0 minus is 0 amps because no current will be able to flow through the open circuit terminals of the capacitor. We can determine IL at 0 minus just by using Ohm's law, really. So this 12-volt drop is going to occur over this 1 ohm resistor in series with this 5 ohm resistor since IL can't branch off and flow through the open circuit. So that's going to be 12 volts divided by a total series resistance of 6 ohms gives us 2 amps. And for our capacitor voltage, VC at 0 minus, the capacitor voltage is the same as the voltage drop over the 5 ohm resistor. So that's going to be 2 amps times 5 ohms gives us 10 volts. So this is the result of our circuit analysis at t is equal to 0 minus. Now we will analyze the circuit at t is equal to 0 plus. So at t is equal to 0 plus, our switch is opened, our 5 ohm resistor is taken out. So we simply have our 12 volt source in series with our 1 ohm resistor. At this particular instant in time, because the inductor current cannot change abruptly, I'm going to replace my inductor with a 2 amp current source directed to the right, such that the inductor current IL of t must be 2 amps, and it has the same direction as I've defined IL. My capacitor, I'm going to replace that with a 10 volt source such that VC at 0 plus must be 10 volts. And let's define our capacitor current here, IC at 0 plus, and our inductor voltage VL at 0 plus. So by inspection, IL at 0 plus must be 2 amps. Since IL at 0 minus was 2 amps, IL at 0 plus must also be 2 amps. VC at 0 plus is 10 volts. Because if VC at 0 minus was 10 volts, VC at 0 plus must be 10 volts. We can see that IC at 0 plus is 2 amps. And that's because if we have 2 amps of current flowing here, and everything is connected in series, then all of our currents must be 2 amps. And lastly, we need to figure out what the inductor voltage is. So if we know that 2 amps flows through this 1 ohm resistor, and it's flowing into this terminal and exiting this terminal, then we know that there is a 2 volt drop over the resistor, positive polarity on the left, negative polarity on the right. So if we wrote a KVL equation, we would see negative 12 volts plus 2 volts plus this quantity plus 10 volts is equal to 0. So negative 12 plus this guy is equal to 0 means VL at 0 plus is equal to 0 volts. Equal to 0 volts. Alrighty. So the next thing that we need to do is analyze the circuit at t is equal to infinity. And again, this is because this voltage source was not removed from our circuit. So we are expecting values for at least one of those 4 parameters to be non-zero. At t is equal to infinity, our switch is still open, and it's been open for a long time, such that any transient conditions have died out, and so we should replace our inductor with its steady state equivalent and our capacitor with its steady state equivalent, which gives us a 12 volt source in series with our 1 ohm resistor, in series with a short circuit, which is representing our inductor at t is equal to infinity, in series with an open circuit, which is representing our capacitor at t is equal to infinity. And by inspection, we can see that VL at infinity must be 0 volts. The voltage drop over a short circuit must be 0. IL at infinity must be 0 amps because no current can flow through the open circuit that's representing our capacitor. IC at infinity is 0 amps. And lastly, VC at infinity must be 12 volts because there's no voltage drop over the inductor or over the resistor. So we can write down these guys in our table. VC at infinity is 12 volts. IC at infinity, 0 amps. VL at infinity is 0 volts. And IL at infinity is 0 amps. So these are all of our conditions that we are going to use to help solve for the coefficients of our response equation. Because our circuit is critically damped, our capacitor voltage will be of the form A1 T e to the minus alpha t plus A2 e to the minus alpha t. And again, because we are having a total response problem, we must also include the contribution at t is equal to infinity. So this will be plus VC at infinity. At t is equal to 0, our first term goes away because A1 times 0 is 0. Then we're going to have A2 times e to the 0, which is 1, plus VC at infinity, which was 12 volts. So this gives us VC at 0 plus, which is 10 volts, is equal to A2 plus 12 volts. A2 must then be equal to negative 2 volts. Our inductor current, our capacitor current, IC of t, will be of the form C dV by dt, which will give us C negative alpha A1 e to the minus alpha t plus A1 minus alpha A2 e to the minus alpha t. We're taking the derivative of this guy, so we don't have any at infinity term because the derivative of this constant term is 0. So at t is equal to 0 plus, we see that this simplifies to C multiplied by A1 minus alpha A2. So that's going to be C is 2 farads, where a farad is an amp second per volt. Now we're multiplying by alpha, so that's 1 units of per second. These guys cancel each other out. A2 is negative 2 volts. Volts cancels here. So we see that we have 2 amp seconds per volt times quantity A1. Negative 2 times negative 2 is plus 4 amps. And this is going to be equal to IC at 0 plus, which is positive 2 amps. So we can see that A1 is 2 minus 4, negative 2 amps, divided by 2 amp seconds per volts gives us negative 1 volts per second. Those units, a volt per second, might seem confusing, but if we look up here in our original equation, we're expecting to get volts. So this quantity A1 is being multiplied by time, measured in seconds, so it makes sense that A1 has units of volts per second, since the exponential bit will not have any units. So if we know what A1 is and we know what A2 is, our capacitor voltage is then simply A1, so that's negative 1 t e to the minus alpha, which is 1 t, plus A2 minus 2 e to the minus alpha t, plus VC at infinity, which was 12 volts. And there we go. This is the total response of the capacitor voltage. Since we know A1 and A2, we could easily solve for our inductor current just by substituting in C alpha and A1 into this expression and C A1 alpha and A2 into this part. And we could find the inductor current in a similar methodology and then use that to find the coefficients for the inductor voltage as well. So hopefully this seems pretty straightforward. The only changes that we made versus a natural response problem were analyzing the circuit at t is equal to infinity and then making sure to remember to include whatever our quantity of interest, whether it was the capacitor voltage or the inductor current, goes to at infinity in our first equation that develops our system. Other than that, the methodology is the exact same as we've done previously. Thanks.